on the contrary, this is a bit more than bonbon size, so I'm going to try and get through it all in the 8 minutes. Thanks for the introduction. So, energy management is really important. We all know that battery life on phones sucks. You've got to put your phone on the charger every couple of days, otherwise it dies. In the data center, it's important too. Data centers consume a huge amount of power, and of course we have to cool the data center as well, and that consumes power too. So you often pay for your power consumption in the data center twice. So even a small reduction in the power consumption in the data center is going to give us a large improvement in energy efficiency. So what do we have to use? Processor manufacturers have given us the tools to change the way processors use power. The first one that I'm going to introduce you to, you're probably aware of it, but some technical details. It's called DVFS. It basically allows you to change the performance of your processor by reducing the frequency, and at the same time you can reduce the voltage, and that gives you a reduction in power consumption, or power draw. Now, the power consumption of a processor is actually made up of two components. The first one on the left there, that looks a bit more complicated, is the dynamic power consumption. And that's what's used when transistors are actually switching. And it's got a V squared term in it, so if you can reduce the voltage, you get a reasonable reduction there. The other term is the static power consumption of the processor. And this is determined by the size of the transistors that are used to construct it and various other factors. And that also depends on V, but it's not V squared, so you don't get as significant a reduction when you reduce the frequency. Now, I presented at Hot Power last year and told everybody about how DVFS is becoming less effective. And that's because static power is increasing, so the right-hand term is going up, and the left-hand term is actually going down. As we get smaller transistors, we can use smaller voltages. And the static power actually increases exponentially. So you get this problem where the diminishing returns from reducing the frequency mean that you don't get as much energy saved. And better memory performance is actually also having an effect on this as well, because single-threaded workloads have a much wider pipe which they can access memory, so there's fewer opportunities to scale the frequency down without significantly impacting their performance. What else do we have? We have low power idle states, or C states. Now, these are becoming much more effective. Processors often come with numerous idle states, which allows you to choose the level of sleep to go into. And they have very low power consumption and also low transition overhead, so you can use them frequently without impacting your performance too much. So on a Core i7, power consumption of the total system sort of looks like this. In the C0 state, which is the active state, your power consumption depends on the frequency at which the CPU is operating. But in the other states, it's frequency independent. So if you can get into the C6 state, you can save up to 60, a little bit over 60% of the total system power. Now, that's if all the cores go into the same state. This graph shows what you get if only certain numbers of cores go into that deep sleep state. You can see when all of them are in that C6 state, you get an extra jump down in power consumption. So it's best if we can get all the cores into that low state. So a trade-off is presented: do we slow the CPU down or do we put it to sleep? It may not be an or question, it might be an and or question. How do we optimize energy? If we reduce the CPU's frequency, it reduces the power draw of the CPU, it increases execution time, and that means that energy is not necessarily reduced. And it also reduces the time that we can spend in an idle state, so it's definitely a trade-off. If we go to sleep, we keep the processor running fast, execution time is not significantly affected, there's a little bit of overhead, and the energy consumption depends on which idle state we go into. So how do we test this? Run a few benchmarks, or a couple. Apache, just a simple HTTP workload, and the other one's just decoding an MPEG stream and playing it back. They're common examples of real-world workloads that you'll often see on servers, desktops, and mobiles. And they're bursty, which means that the CPU can actually sleep. It's not like spec CPU where the CPU just goes 100% the whole time and then there's no opportunity to sleep. So what does the setup look like? We've got the system under test in the middle, coordinator which records the power consumption, a control network, and for the HTTP benchmark we've got this load generation bit on the side, which is its private test network, and some clients which generate the requests. Let's take a look first at the MPEG decode. This is what it looks like when you scale the frequency down. What happens to CPU utilization on the Core i7? It's single-threaded, so as we reduce the frequency, obviously the the execution time goes up, but there's not much overhead because the idle state transition is quite low. What about energy? Energy comes down, but as we use the deeper idle states, DVFS is becoming much less effective, and the line at the bottom, which is C6, is almost flat. There's no difference. Moving on to web servers. Google did the study. They found that most web servers actually spend most of their time 30% utilized. So that's what I'm aiming for. This is what the load looks like as we reduce the CPU frequency. As you can see, there's a bit of overhead when we use C6. What about energy? Well, you can see DVFS is actually helping us a bit here, even when we use the deep C state. And that's because not all of the cores are going into that C6 state, which means you don't get that extra jump as you go right down into the C6 state. How does it affect our throughput, though? Throughput's not affected for this load. So we can reduce the CPU's frequency, and our request efficiency in requests per joule is actually maximized if we use the deepest sleep state at the lowest frequency. So this is an underutilized system. Obviously, if it was utilized, then we may lose some throughput, but as Google showed, it was most of the time you spend your time underutilized. What about response time? You might expect that if we reduce the frequency and add some latency to the sleep state transitions, you might lose some response time. But it turns out that you don't really lose it. The overhead is much smaller than the network latency, and this is actually a local area network, so the network latency is already pretty small. If you go to an internet connection, for example, that noise is going to be even smaller. And in the paper, I also did a comparison with some embedded platforms. So I'm just going to stick those on the graph of request efficiency. There's the Core i7 quad-core. If we put a Panda board, which is an ARM processor, OMAP 4430, we're getting much less request efficiency. What about Atom? Atom in the data center is a big topic these days. It's about the same as the Panda board. This is quite a surprising finding for me. So what are the take-homes? DVFS on the cores is becoming much less effective as C states get better. In lightly loaded systems, you can reduce the frequency and use the deep C states and not lose any throughput or latency. The high C state transition rate with the Apache workload increases the overhead, but it doesn't change your response latency. And as I said, we can reduce the frequency of the CPU and actually gain something in the data center for an underutilized system. And desktop class gives you the best energy efficiency, and it turns out that Turbo Boost is not energy efficient in this case. What am I concluding? Well, CPU power management is changing direction. DVFS is becoming less effective when it's used on the cores. Maybe we need more control, like control the frequency of the caches, maybe the memory controller or memory itself. What about other links on the system? And minimizing idle and static power is much more important for these sub-micron processors, and it's critical for phones where they spend most of their time asleep. So, questions? We have time to clap. Tick tock.
So why do you think the embedded processors are doing so bad on this load?
So I should have added a caveat there. The embedded systems that I was testing definitely weren't designed for high throughput network workloads. The Panda board actually uses a USB connected network interface, so it's not going to get the best throughput. There's actually quite a high interrupt latency for the USB network interface, so I think that's contributing to that problem. There's definitely other factors as well. Which yeah. Thanks.
Well, one more question, if you have time.
Yep.
A second question, Eddie Kohler, UCLA, Harvard, I guess. So you're advising that we need more control. Do you think that that control will eventually become equally unimpressive as frequency scaling has become?
I think it depends what the process is aimed at. If the process is aimed at a phone, then static power consumption is really critical, and it's critical to reduce that leakage power or implement better sleep states, whereas on the desktop or server processors, you don't spend as much time idle. Well, you probably don't spend as much time idle like with all the cores in the idle state. So there's definitely going to be some form of active power management required. And that's what DVFS allows you to do.
Great.
Okay, thanks.